Thank you very much.
Okay, yes, so I'm very happy to be here. I'm now going to take control of the screen. Okay, it's I think it's going to let me do that now. Yep. So now it should be sharing, and I'm going to go into the PowerPoint presentation mode. Does that look good? Can you see my first slide?
Yes, we can.
Okay, good. Yes. So I've got around a dozen slides or so. I didn't actually count them, but I've got about a dozen slides to talk to. I like webinars like this to be conversational, so I'm really pleased at the idea that people can submit their comments through the chat and that Dan will bring them up right away. So I want to encourage that. I'm going to talk some about STARS Technology Corporation, the company that I and others started in 2016 as a spinoff from the activities we had going on at the Pacific Northwest National Laboratory, where I was an employee and a technology developer. Everything I'll talk to will be relevant to, if not directly, but at least relevant to the hydrogen hubs, and very specifically also the desire for a Pacific Northwest hydrogen hub to be formed. The image on this screen, the background image that's a little out of focus, is a compressed natural gas filling station in the Los Angeles area. The company that's been funding us to the greatest degree for our effort is Southern California Gas Company. And they had us make a slight Photoshop type change to the picture so that it says SoCal Gas Hydrogen instead of compressed natural gas. Their interest is in becoming a sustainable fuels and chemicals company. I think that's probably the wrong way to put it. They want to become the sustainable gas company. And the image in the foreground on the left is a microchannel reactor. That's the disk on the bottom left. I don't know if my pointer is showing up, but I'm trying to highlight that. Right above it is a microchannel heat exchanger. These are chemical process chips, which we developed over the last 25 years at PNNL. Like computer chips, chemical process chips are highly intensive. In fact, for the process rates through these devices, we're about 100 times higher per unit hardware volume than conventional chemical process technology, which we've all come to know and understand through marvelous infrastructure additions in the 20th century. But this is very advanced. So again, it turns out shrinking the devices in the way we do increases the intensity by a factor of about 100. And you can see in the bottom left, it shows that disk is about 11 inches in diameter. So now if there's one thing I want everyone to remember is that we believe our technology provides a fast, possibly the fastest way to a cheap, clean hydrogen grid. And again, that's highly relevant to the hydrogen hubs. So I will go on to my second slide. So if I want to talk about getting a hydrogen grid, I need to explain it. We think it's based upon combining our units, our hydrogen generators, as chemical transformers on the gas grid. So just like electrical transformers sit on the electrical grid and enable us to recondition the electrons, we would be reconditioning the molecules to make hydrogen from natural gas and water in proximity to the place where the hydrogen is needed, for example, hydrogen filling stations, or ammonia plants, or steel refineries, or a lot of other types of locations. And this also includes distributed power generation. I'm showing on the left a map I'm sure everybody here has seen many times, a map of the US interstate and intrastate natural gas pipelines, but of course the distribution pipelines would cover the map. And we all know that there's already trillions of dollars invested in natural gas infrastructure. By placing units as chemical transformers on the gas grid, we make continued use of the gas infrastructure. As you all know, seasonal energy storage is already built into gas. The methods for cost recovery are already defined and in place. The customer bases include large energy users. And now renewable natural gas gives us an opportunity as well. And particularly with renewable natural gas, we get an opportunity to go carbon neutral and carbon negative for the hydrogen that we would produce. So the California Air Resources Board now, you may know, has commented that all natural gas vehicles in California are now carbon negative. All 300 plus CNG filling stations are receiving renewable natural gas. Much of this is from agricultural methane that would have been released to the atmosphere. So capturing the methane and converting it and putting it to use so that its CO2 is a carbon negative step. And last year, all the filling stations have gotten that way. So, and at a low cost. So this is an exciting development, but it's also the feedstock for carbon negative hydrogen from our system. And I'm going to jump around on things today. So this is a list of topics rather than an exact outline. We're going to talk about hydrogen and hydrogen applications. We're going to talk about the hydrogen hubs. I've listed classes of hydrogen, though I'm just going to right now simply say, I think probably everyone knows about the various notions of colors of hydrogen: green, blue, gray, turquoise, gold, et cetera, hydrogen. And carbon intensity of hydrogen. Hydrogen is a fuel like other fuels, which the making of and the use of leads to some CO2 emissions. Renewable hydrogen is another category for hydrogen, another adjective in front of it, and clean hydrogen is a newer one. I'll talk more to that in this presentation. And I'll talk more about the hydrogen generators. I've already mentioned that we're using advanced microchannel reactors and heat exchangers, chemical process chips. But I'll also point out that our hydrogen production system is electrically heated, whereas conventional steam methane reforming requires that you burn more of the methane to provide the heat. And this also allows us to reduce the carbon intensity of the hydrogen. I think these are opportunities for the natural gas distribution companies to be heroes as we decarbonize our economy, and opportunities for the Pacific Northwest, including the hydrogen hub. So let's get into that quickly. I want to talk a moment about regional clean hydrogen hubs as envisioned by Public Law 11758, passed by Congress near the end of last year and signed by President Biden in the middle of November. It's also called the Infrastructure Investment and Jobs Act, sometimes the Bipartisan Infrastructure Act. It has $9.5 billion in funding for clean hydrogen production technologies and infrastructure. $8 billion of that is designated to be used by DOE to establish at least 4 regional clean hydrogen hubs. I'll show in a moment a little bit more about what that means. And it has a standard for clean hydrogen that says it's clean hydrogen if the hydrogen is produced with a carbon intensity equal to or less than 2 kilograms of CO2 equivalent emitted per kilogram of hydrogen at the point of production. So I think that one of the questions that came in already asked about how is this a reduction in CO2 emissions? So I will say that about 97 to 98% of the hydrogen produced in the world today is produced by conventional steam methane reforming with a carbon intensity of around 9 to 12 kilograms of CO2 emitted per kilogram of hydrogen produced. So you can see that a requirement that they call a clean hydrogen that says that you've got to get the CO2 equivalents to no more than 2 kilograms per kilogram of hydrogen is in the neighborhood of a 75 to 85% reduction in the CO2 emissions. Now, the image I've just added, I stole it from a screen as a screenshot from a presentation from the Department of Energy early last week from their annual merit review, a presentation on their efforts to provide what's required by the public law. So they point out some things about what the law says. So I'll start off in the upper part. The clean hydrogen production standard is what we just talked about, the 2 kilograms of CO2 per kilogram of hydrogen production. The hydrogen hubs are to demonstrate production, processing, delivery, storage, and end use of clean hydrogen. And the hydrogen hubs themselves are intended to be developed into a national clean hydrogen network to facilitate a clean hydrogen economy. Now, at this part of their image, they point out something that's required by the Act. At least one of the hydrogen hubs has to be making hydrogen from fossil energy. At least one has to use renewables for hydrogen production, and at least one has to use nuclear power. For applications, they say the hydrogen hubs, at least one has to provide hydrogen for industry. This could be things like steel refining. In fact, a lot of things that are industrial. Another one, at least one, doesn't have to be a different one, has to have power generation as one of the uses for the hydrogen. And at least one has to have residential and commercial heating, and at least one has to support transportation. So on this sort of a diagram, this semi-schematic, they show, again, the sources of the energy and the feedstocks, and they show the notion of a clean hydrogen production facility. What I'm talking about for our system, though, is distributed hydrogen production on the gas grid. So it would look a little bit different than this. But that gives you a sense of what it is they're looking to. And by the way, in the meeting a week and a half ago, they stated, and they also rolled out a draft solicitation for proposals for these regional clean hydrogen hubs, where they said they're actually anticipating that there might be anywhere from 6 to 10. So more than the at least 4, but anywhere from 6 to 10 regional hydrogen hubs. And that actually means there's pretty good odds that the Northwest could get a regional hydrogen hub. And if each one had, let's say there were 8 of them, if each one had the same amount of money from the DOE, that's $1 billion for the hydrogen hub in the Northwest, though there is also cost share requirement. Now, I said I'm going to jump around a little bit. So I'm jumping quickly to what STARS has been focused on as the first application for hydrogen, transportation. And I'm sure everyone here knows that in the Northwest, transportation is the leading source of CO2 emissions. If we want to make a reduction in CO2 emissions, we've got to make sure we're tackling transportation. And one of the things I'll point out about why hydrogen matters is there really are strong limitations on battery-powered vehicles. I've had 2 plug-in vehicles, and I really love them. It's so convenient to just at my house to be charging them overnight with cheap power, cheap, clean power. I think in the Northwest, we can think of ourselves as the cheapest, cleanest electricity in the country, with only a few small locations that might be cheaper. We think electric propulsion is the future, but of course that can be battery-powered vehicles or fuel cell-powered vehicles, and we think it will be both. So notwithstanding the convenience of charging at home, there are many applications where charging at home is not the economic value proposition. Long-haul trucking is an example. Railroads, shipping, air transport, et cetera, are not examples of that. And so we think fuel cells are going to be very important. And you might be aware that fuel cells have recently, in the last few years, gone into mass production. The PEM fuel cells are in mass production with companies like Plug Power. This is because it has turned out to be cheaper to run warehouses, forklifts in warehouses with hydrogen and fuel cells than to use batteries. So Amazon and Walmart are changing out their forklifts for economic reasons. So I'll say STARS intention. STARS was formed in 2016, long before the hydrogen hub topic came up. Working with Silicon Gas, our entire focus has been on providing hydrogen that is economically preferable to other fuel sources. So I'm delighted at the notion that that the warehouses have realized that the forklifts have an economic value proposition by converting to hydrogen. And as I said, this has allowed fuel cells to go into mass production. Yes, Dan?
Bob, I have a question, actually. Will you talk a little bit about the technology itself? I mean, so I know it's focused on producing hydrogen off the gas pipeline system, how that hydrogen gets to a pump, like we see here, those are the kind of mechanics I'm at least interested in. So
I sure will. As I said before, it's kind of hard for me to work to an exact outline. I feel like I'm jumping around a little bit, but it's because there's so many different things to have to cover, but I sure will. I've got some slides, in fact, where I show the hardware. So we believe we've got a strong approach to get in the near term to clean hydrogen at under $5 per kilogram. The barrier today, the last bullet on this says, the barrier today is that in California, which has done the most to get hydrogen for fuel cell vehicles in place, is that at the filling stations, it's about $15 a kilogram. That is because the cheap hydrogen is currently produced in central facilities and then transported at a cost of $8 to $10 a kilogram to the filling station. So by the way, a kilogram of hydrogen has about the same energy content of a gallon of gasoline. So when I say $15 per kilogram, you could think of that as $15 per gallon. But please note, hydrogen fuel cells are about twice as efficient as a standard internal combustion engine. So to the person driving the car, $15 a kilogram might feel more like $7.50 per gallon. But by the way, nobody really believes that that's an acceptable price for hydrogen. Getting to under $5 per kilogram would be like buying gasoline at $2.50 per gallon. So again, we think we've got an approach that will lead to very cheap hydrogen that is also matches the clean hydrogen standard. So this is part of the information about what the rollout could look like. So the image in the upper left is a snapshot from SoCalGas's service territory. We're going to be doing a demonstration this summer at Sunline Transit Agency, and this is a picture from their site. They've got 16 hydrogen fuel cell buses, and they've got a water electrolysis system that was paid for largely by the state of California, but they are very interested in cheaper hydrogen, and that's, I believe, part of why they agreed to be the site for our demonstration. I have placed additional green hexes at locations where SoCalGas has CNG stations. As I mentioned before, there are actually more than 300 CNG stations in California, but most of them are owned by others, not by natural gas utilities. As I mentioned before, clean hydrogen can be based on renewable natural gas, and that gives us carbon negative hydrogen production. Let me go on to the next slide. So now I'm going to jump back a little bit on hydrogen and a little bit more about why. And this has to do with energy density. So I've said here, batteries can't do everything. This is an Airbus concept for a blended wing passenger vehicle. The comparison I want to make for everyone is that if you wanted to fly, let's say from Seattle to Europe on a 747 loaded with people, 30% of the mass of the plane at takeoff is jet fuel. If you want to go the same distance with the same number of people, et cetera, you need 30 times that mass in batteries. And what that means is that you can't get off the ground because you don't have that much lift, not close to enough lift from the wing in that. Well, hydrogen is 1/3 the mass of the jet fuel. And so the result is a liquid hydrogen fueled airplane doesn't need as much lift, so it doesn't need as much wingspan, so it doesn't have as much friction, so everything gets more efficient and cheaper. So companies like Airbus are now working their concepts they've wanted to do for a long time, because the world has started to realize that hydrogen is real, and that for long haul trucking, for aviation, for a lot of other things, that it's going to be the economically preferable way to decarbonize. And then on my next slide, I show some of these others. I'm showing shipping, I'm showing long haul trucking on the right. On the left is an ammonia production plant, and on the right is a steel refinery. Hydrogen gives us opportunities to do that, decarbonizing those operations as well. And now I'm going to talk a little bit about the technology. I think I've got about 3 or 4 slides on the technology now. So the origin for our work, again, is at the Pacific Northwest National Laboratory. I and some others started work on these things a little more than 25 years ago. In fact, the picture on the bottom left is 29 years old. This is a microchannel heat exchanger, one of the first ones we built at P&L. A microchannel heat exchanger has channels where the width of them are less than 1 millimeter wide. And it turns out that the extreme heat transfer rates we can gain in such thin channels give us the process intensification that I discussed in my opening. We get about a 100-fold increase in the heat transfer total duty per hardware volume by going to engineered microchannels. And for chemical reactions that are heat or mass transfer limited, we get the same advantage. And likewise for chemical separations in that kind of a case. So on the right-hand side, I'm showing an example from NASA. So in the late 90s, NASA started funding us at P&L to begin working on concepts for Mars. NASA did not want to have to ship all the propellant to Mars for robotic or human return missions. They want to make the propellants on Mars. If you saw the movie The Martian, That is why there was an ascent vehicle sitting elsewhere for Mark Watney, the astronaut, to drive to. It was already sitting there and already fueled so that he could get rendezvous with the spacecraft that was passing by. There's quite a bit in the book on propellant production on Mars, a lot less in the movie on it. So we were working CO2 capture from the Martian atmosphere. We were working reactors and heat exchangers as well. And by the way, with the most recent lander on Mars, there's a small propellant production plant which uses a microchannel heat exchanger, much like the ones we first started building, in fact, in the late 1990s. So this stuff has made it to Mars now. Now, the next part for us was, what can we do for Earth? In fact, a NASA program manager asked me in the early 2000s, if we can do this with solar energy on Mars, why can't we do it on Earth? And we can. And so we're showing on the left-hand image an array of microchannel reactors and heat exchangers, over 20 reactors and heat exchangers in a hydrogen production plant. This was our second microchannel hydrogen production unit. This was the one designed to be highly efficient, along with being process intensive. In the middle view, we used concentrated solar energy from a parabolic dish to provide the heat for the endothermic steam methane reforming reaction. This is the system that sits inside the nacelle that's at the focal point, and this is that chemical reactor, very much like the reactor on my opening slide, and this is the nacelle with hardware inside. So we took a Stirling cycle, a dish Stirling system, removed the Stirling engine, put our system in place, and achieved world record 70% solar to chemical energy conversion efficiencies. We've done a similar kind of thing with electrical heating for our systems now too. In fact, we're now at 80% electrical to chemical energy conversion efficiency with induction heating. The induction heating system is easily world record. The highest anyone else has done for steam methane reforming with induction is 22%. So we have really demonstrated that with the microchannel architecture and induction heating, we get high efficiencies. I'm not going to talk all the way through these. I just want to give you a sense that in the 1990s, we started working the chemical process chips and systems based upon them. In the 2000s and the early 2010s, we were working systems. In the late 2010s, we were also working additive manufacturing. It looks like there's going to be another question, or was that just another person coming in?
I think that was just another person coming in. I think they're
Okay.
moving now, so we're good to go.
We also were improving the design of the chemical process chips. And this image on the right from the year 2020 was our first CAD version of the system that we're currently assembling, and I'll show a picture of that in a minute. So this is based on over $50 million in R&D projects at PNNL. As I said, STARS was formed in the year 2016 so that we could accelerate getting this stuff into the marketplace. So again, these are process-intensive chemical processing chips. In this image, I show the chemical process skid itself that we're assembling to take down the sunline. It'll have 3 of the microchannel steam methane reformers, multiple microchannel heat exchangers, and other chemical reactors too within this piece. This has about a 1 square meter footprint. We call this the half-hex. It's designed to have a mirror image associated with it, and from the top, it's hexagonally shaped. I guess at the moment, since it's cut in half, it looks like a trapezoid from the top. But the 2 halves together should be able to produce about 165 kilograms of hydrogen per day with a 2 square meter footprint. So these are part of the circuit panels that are associated with that. And this shows you the technology. Again, the same kind of picture I had before, but now we've simply placed on top of the reactor one of the induction heating coils that we're using. So if you're familiar with induction heating cooktops and things like that, it's the same kind of approach. A copper coil induces an electrical current into the reactor. Joule heating produces heat. So we are, without touching the reactor, we actually have a gap of 1 centimeter between the coil and the reactor with insulation within that. Without touching the reactor, we're able to rapidly heat the reactor and get the heat in to drive the endothermic steam reforming reaction. And what this means is that boost that we get We have an increase in the higher heating value of the stream because it's an endothermic chemical reaction. That boost came from chemical energy. I'm sorry, came from electrical energy that went into the system. And against a clean hydrogen standard, that's not CO2 produced at the point of production. So that makes it even a little bit easier for us to be able to get to the clean hydrogen standard. And renewable natural gas, as I said, we get to carbon negative operation. So that is a substantial decrease in the carbon intensity of the product hydrogen. So this is just a little bit more now quickly on.
One question, Robert, on your previous slide, again, coming from me.
Sure.
So does the use of electricity in every case reduce the carbon intensity? Where I'm going with this obviously is sort versus site, right? At the site, yes. But what's the source of the electricity? If it's coal, does that make a difference? If it's natural gas or hydro or wind or solar, how's that all work out?
It really depends upon which definition of hydrogen colors, renewable or clean hydrogen we use. Dan, so in the Bipartisan Infrastructure Act, it simply counts as CO2 emission at the place of production. So it doesn't matter where the electricity came from there. But if you go to Washington State's renewable hydrogen bill, to call it renewable hydrogen, it can't have been coal that produced the electricity. It's got to be carbon-free electrical power in that kind of a case. So to qualify for the hydrogen hubs, coal would be allowed for the electricity, but if you're using coal or methane at the point of production, then the CO2 emissions from that would count. So by the way, if you're doing conventional methane steam reforming, I said that has a carbon emissions of 9 to 12 kilograms of hydrogen, of CO2 per kilogram of hydrogen. So to hit the 2 kilogram per kilogram standard, you'd have to capture in the neighborhood of 8 or 9 or 10 kilograms of CO2 for each kilogram of hydrogen and do something else with it. To do it with renewable natural gas, you don't have to, because the renewable natural gas gets scored as having negative carbon intensity. I know that's a little confusing, but it depends on whose rules, just like whether it's the Washington State income tax. Well, actually, we don't have an income tax in Washington State. So, but just like income tax in some states have different rules than the federal income tax.
So I do have another question. Thank you for that. And while I get ready to prep this question, I just want to remind folks, please do use the chat function to enter your questions. From Kevin Duell at Northwest Natural, does the electric SMR release CO2? Steam methane reference, electric steam methane reforming release CO2.
The first versions of our system will release CO2, yes, because CO2 is formed in the steam methane process. But as I said, conveniently, it doesn't count as CO2 against the clean hydrogen standard if it's renewable natural gas. Now, because with renewable natural gas, it is strongly carbon negative, we should really be able to blend fossil natural gas and renewable natural gas together. And roughly a 50% blend would take you to about carbon neutral. So they would score as roughly 0 kilograms of CO2e per kilogram of hydrogen. With a bit higher efficiency and a few other things, we might be able to get as much as 3/4 fossil natural gas blended with renewable natural gas. But yeah, there's CO2 emitted, but again, when it's renewable natural gas, it's scored as negative because otherwise there would have been methane emitted elsewhere. So that's an advantage we have with the clean hydrogen standard.
Thank you, Bob.
Sure thing. So this is a little bit about the STARS team. Again, I said this is somewhat about STARS Technology Corporation. So I'm the guy in the upper left. You can already see my image from this presentation. Dennis Walters was at the meeting last week. Daryl Brown is the third of the three of us that are engineers on our team. We've got 2 other people that are principals as well that have business degrees. One of them is an intellectual property expert. On the right, we're showing advisors. Ron Kent, it was formerly the Advanced Technology Development Manager at SoCal Gas. He retired last year and joined us as an advisor. Bill Reedy is a veteran space shuttle pilot. Bill is ex-Navy, then went to NASA to fly 3 shuttle missions. He moved up in NASA and became the associate administrator for the Office of Spaceflight, which meant that the $6 billion set of activities per year for all the space shuttle missions, everything at the Kennedy Space Center, the Stennis Space Center, and the Marshall Space Flight Center were under his office, and the assembly of the International Space Station. And Bill is the guy who advises us on hydrogen for aviation because he knows that topic so well. And he reminds me there's a reason why we used hydrogen in the space shuttle rather than doing everything with batteries. And it has to do with that we couldn't have gotten off the ground. So on the bottom, by the way, we're listing companies that are partners or in our value chain. SoCalGas and Sunline on the left are partners with us for the demonstration. Pacific Northwest National Laboratory and Oregon State Universities are partners with us for continuing to develop and improve the technology. And companies like Highline Engineering, they're the ones assembling the system. The picture I showed of the system being assembled. Concept Systems here in the Tri-Cities is a control system company, and VPE and i3D are additive manufacturing companies. They built the reactors and heat exchangers, and EGO, the induction heaters.
Great. Bob, I do have another question here, an engineer's
Sure.
question for an engineer. And I'll ask you maybe to kind of just do this briefly, but and if this, I'll encourage this questioner to reach out to you directly if your explanation doesn't scratch his itch. Could you please elaborate a bit on how a chemical process chip does what it does and where it fits in the miniature reactor?
Okay. Well, yeah, let me come back then to this image. So this is the reactor, and we call it a chemical process chip. This has about an 11-inch diameter, and it's a little less than an inch tall. So this is a chemical process chip. The channels in this are millimeter type widths, and some of them are less than a millimeter in width. This heat exchanger is a counterflow microchannel heat exchanger. All channels are less than a millimeter in width. So we bring in steam and methane at about 300 degrees C and preheated further to nearly 700 C before it goes into the reaction. So it's almost hot enough for the reaction temperature we want. We take the product stream, the synthesis gas stream that includes CO2, a little bit of unreacted methane, a lot of unreacted water, and the hydrogen. We bring those back through counterflow and cool them down. So that's how we do the preheating. So that's a little bit more on that. I should mention, though, that the catalyst channels in this, the chemical reaction channels in this reactor have catalyst material within them. There are also heat exchange channels within this that do not have catalyst within them. So I hope that answered enough of the engineering question, but I know that if it didn't, there's opportunities for more questions. So this was intended to be my last slide, though I do have a couple of backups if they turn out to be appropriate. So I'm showing again this snapshot for part of the SoCalGas service territory. I think I need something like this for the Pacific Northwest to be showing how we can be placing our units on the gas grid in the Northwest. And I should mention also, I didn't say it before, the black lines look like highways, but they're not. These are the distribution these are the transmission lines, the higher pressure transmission lines through this slice out of the SoCalGas service territory. And as I said, I placed in this case our units at each of the CNG stations that are within this slice that are owned, each station owned by SoCalGas. Again, there are actually about 300 such stations in California. So finally, I'm going to say, I think we want a similar vision for the Pacific Northwest. Combining the assets that we have, we certainly have nuclear power, we have renewable assets, we have fossil assets coming through the state. We have the ability to say we're making use of all of the feedstocks and feed energy required for a hydrogen hub. Again, transportation is our biggest CO2 emission. At least one hydrogen hub has to make hydrogen for transportation, but I believe we should, in parallel with that, be working distributed power generation. As fuel cells go into higher mass production volumes, their costs come down. They will become very suitable for distributed power and heat generation. supporting microgrids, and again, heat for buildings too. So I think we have an opportunity to be deploying in a distributed manner, making use of the gas transmission infrastructure throughout the Northwest without having to build hydrogen pipelines to be able to get hydrogen to the points of use. So we have the opportunity for a rapid deployment. That's sort of my real bottom line to it. So any questions now are also certainly welcome.
Yep. Please do take a moment to enter any questions you have into the chat. And while that's going on, Bob, I'll ask another question here. So what I'm seeing here is you cite these facilities, you cite your reactors on the gas pipeline system where there is an immediate and adjacent demand. So you're eliminating the need to transport the hydrogen from one place to another. Is that correct?
That's absolutely right. So by the way, central hydrogen production, that's 97, 98% of the world's hydrogen, comes from conventional steam methane reforming. And the cost of producing hydrogen that way at this central facility is about $1 to $2 per kilogram of hydrogen. So very low cost. It's putting it in tube trailers and driving it elsewhere that elevates another $8 to $10 per kilogram. And then there's a few dollars per kilogram for compression and storage and dispensing at the filling station. So that's how it's $15 a kilogram in California. And it's why companies like Toyota are saying to California, why don't we have cheap hydrogen available yet so we can go into mass production? We're working with SoCalGas so that we could get these systems on their grid. I want to put them in the Northwest too, and the hydrogen hub is a great opportunity to do that in the same way that you just described.
Yeah, so this follow-on question then is, are there, beyond transportation, are there other applications? So I'm thinking in particular of industrial applications. Can this technology produce at that scale? Or is it modular in nature? You know, how do we get to that? Number one. Yeah, well, I'll just leave it at that. And then I do have another question in the chat for you.
And part of the answer to that is yes, there are other applications also here in the Northwest. So a part of it is to look at our system and to start thinking of it as being kind of like a supercomputer. It's a super chemical processor. In order to have 500 kilograms per day at the hydrogen filling station, you'd put 3 of those full hex units there. To get to 1,500, you could put 9. But I can also imagine that at the point where that would be of interest, that we could be designing the architectures a little bit differently than just the hex type approach that's under 65 kilograms per day. So ammonia for fertilizer is an important use of hydrogen today. Today, that's made from natural gas, as you know. There's no reason why we can't use our system in conjunction with transportation to be making lower carbon intensity hydrogen for ammonia production for fertilizer. And I mentioned before also, I really see distributed power generation with fuel cells or hydrogen gas turbines, and some companies are starting to develop those too, as load following units. So when fuel cells become cheap, when there are a couple $100 per kilowatt capital cost, and we have cheap hydrogen available for them, then we've got the ability to locate the fuel cell near the buildings, producing power for microgrids, buildings, and more, but also heat for those buildings for the time of the year when we need the heat. So one thing that I didn't mention is that currently in California, and we will eventually see this in the Northwest, but currently in California, there are times of the year now where the renewable electricity generation for wind and solar exceeds total electricity demand. In fact, I should say that happened last month, where on one date, the total renewable electrical generation accounted for exceeded total electrical demand. And as we all know, that's hard on the grid. It's hard on the power generation systems to be ramping up and down. So if we start to imagine that we're also doing power generation this way, we can take the excess electricity from renewable at a time of day when it would be low price because it's excess at a few cents per kilowatt hour, make hydrogen with it, again, using the same energy storage mode for the filling stations, et cetera. And later in the day, when the sun is lower in the sky or the wind isn't blowing as hard, et cetera, to be driving the hydrogen through fuel cells and selling it back to the grid at more than 10 cents per kilowatt hour. So this is also an opportunity to deal with this inequitable circumstance that's starting in California, but will end up everywhere in the USA otherwise, where we end up with too much electricity some of the time and not enough electricity at other times.
Great. I'm going to recharacterize a question here. I have two more in here. So I'm just going to recharacterize this one. So so if you're generating the hydrogen at effectively the point of use, in the case of, let's say, residential commercial space and water heat, you'd have to get it into a distribution system, right? Are there hydrogen embrittlement concerns in conveying pressurized H2 using the existing pipeline network? That's a broader question, but I'm trying to characterize it in the context of the technology that you're talking about here.
So for items like steel pipelines, not plastic, but for steel pipelines, hydrogen creates an embrittlement question, and it has to be managed just like everywhere else where we run hydrogen through steel pipelines. And we do have steel pipelines for hydrogen in the USA. It means you have a shorter lifetime for the pipeline than you otherwise might have had. In Southern California Gas Company, they're currently also investigating coatings they could put on the inside of the pipeline. Again, it's not a problem with plastics. So a coating added in the pipeline or a pipe pulled through the pipeline that's plastic would be just fine. So one other part answer to it is that hydrogen blending with natural gas is also on the table. An NREL study several years ago suggested that 5 or 10% hydrogen with natural gas would be fine, and in fact would still allow the natural gas meters to do a good job of metering the energy use at the point of consumption. At more than 10%, you get into other kinds of questions with things like natural gas burners. But anyways, I'll say SoCalGas is also considering and discussing with their regulators, discussing a hydrogen pipeline. So one of the things they've got in mind is perhaps going, I don't know if you can see my cursor, but going further inland where there's much more sun, in particular a little bit northeast of LA, with solar photovoltaics to help support this, and then a hydrogen pipeline coming into LA, perhaps with hydrogen distribution, perhaps not. That's a little bit longer, further out sort of a thing. But I see an overall set of answers that says if we can do these things economically, then they're definitely going to have opportunities to happen. If the hydrogen pipelines end up costing too much, then you'd be better off to be moving methane down the pipeline and producing the hydrogen near that point of use.
Okay. Another question here. How does this technology, your technology, differ from a company like Messer that produces hydrogen in bulk for the high-tech industry or high-tech industries? Are you familiar with them?
I don't think I'm familiar with Messer. It rings a bell, but it's not coming to mind. What does Messer do?
According to the questioner, it produces hydrogen in bulk. You may have answered this question previously when you talked about centralized hydrogen production.
Yeah. So again, I don't know if they're doing centralized hydrogen production. Then the difference for us is clear. We have much cheaper transmission of the hydrogen. But again, I don't know what they do. They probably know they might be doing sort of a specialty application with a small system near a point of use where the price point for hydrogen could be very expensive. For example, electrolysis.
Yeah, I'll encourage John to, I'm assuming you'll put up your contact info here, Robert, and if not, John, contact me directly, but I'm sure Bob would be happy to answer your question directly. One last question here. we'll give folks one more chance to enter questions into the chat. But one question that's come in is how does your technology scale up to thousands of kilograms a day applications? So I think this might be a rephrasing of my question around industrial applications.
Right. So for 1,000 kilograms per day, then as opposed to 1 or 2 or 3 Stars 165s, you either go with 6 of those, 6 modular units occupying about 12 square meters, or we would end up designing something that's a little bit bigger that might also be a bit more compact in the way that we put the chemical process chips together. So, but it scales up basically by numbering up, just like computers do nowadays. We scale up by numbering up. We are also considering a newer hybrid chemical process chip that I can't describe for intellectual property purposes, but one where a single chemical process chip might produce 10 to 20 times as much hydrogen as the image on the bottom left on the screen right now. By the way, the bottom right has my email address.
Right. Good. Thank you. That just maybe a related question. You talk about the channels in the processor being millimeters in width or a millimeter or less in width, but that's giant in the context of nanotechnologies. And I think I remember you saying earlier on your presentation that the smaller it goes, the higher the efficiency. Did I get that right? So are you driving towards smaller and smaller channels, just like the computer chip industry continues to strive toward more and more circuits on a circuit board?
Well, that's a great question. And I'm trying to make sure I can do a simple way to describe it. So from the perspective of heat transfer and mass transfer and efficiencies, and also the heat transfer power densities for things like induction heaters, our millimeter and slightly smaller than millimeter scale is close to optimum for getting high efficiencies. But when you talk about chemical reactions and chemical separations, as I'm sure some of the folks online here know, those occur, of course, at the sub-nanometer scale. And so inside our catalyst channels, we have a porous metal structure that allows the reactants to flow through it. But now we're talking transport distances within the porous metal structure that is more like 10 to 80 microns in width. And of course, for the catalysts themselves, the catalysts are nanoporous to begin with. So the molecules work their way into the nanopores and just bounce around like crazy until they finally do their reaction and then find their way back out. So you can almost think of it like the tubing going into the reactor is like the highway. Channels inside the reactor are like streets off of the highway. The porous structure gives us cul-de-sacs, okay? And the nanoporous aspect to that is like individual driveways off a cul-de-sac. So we are putting together an engineered system where we're optimizing at each scale to get the most effective operation. And by the way, this allows us to use a lot less catalyst than what is necessary for conventional chemical reactors too.
That's a terrific analogy. Robert, thank you very much. Just 1 minute, any last questions? We're fast approaching our 1 o'clock witching hour. I'll just remind folks, we have a couple of great webinars coming up. Please go on to the Northwest Gas Association website and sign up for those. I'm not recall, I put them up at the beginning. Let's see, I could probably figure out what they are and just tell you. Here they are. On July 21st, I'll be presenting actually the Northwest Gas Association Outlook study, which we've completed. It's available on our website if you're interested. That'll be probably a shorter webinar, but we'll love to see you Thursday, July 21st between 12 and 1 for the Northwest Gas Association's Outlook study. And then we skip August, but in September, we'll have a conversation with the CEOs of the Oregon and Washington home builder associations talking about affordable housing and energy policy. Should be a fascinating dialogue, and we look forward to having you join us on Thursday, September 15th between noon and 1 for that one. So let me look one last time. No additional questions in the chat. Bob,
Let me make one quick request.
please.
That's okay, Dan. So the quick request is simply, we're looking for others to partner with us for the clean hydrogen hub in the Northwest. This includes gas distribution companies and others. So we sure would like to hear back from people that want to be part of this. Again, we can view it as a substantial federal investment in infrastructure to benefit us all.
Okay, I do have one last question in here. Projections on cost per kilogram of hydrogen, and I think I saw on one of your slides that you indicate you feel confident in a pathway that gets you below $5 per kilogram.
Yes, in fact, that would be the price at the pump. We actually think we can get closer to $3 per kilogram, but at modest hardware mass production rates, we think we can get under $5 per kilogram at the pump. And again, that's like $2.50 per gallon of gasoline.
Okay. All right, Bob, with deep appreciation and thanks for your time today. This is exciting. This is part of why we are working so hard to ensure that the gas energy delivery system remains viable here in the Pacific Northwest. We are confident that innovation and technology will allow us to not only create more efficient applications, but also decarbonize the fuel that the 128,000 miles of installed energy delivery infrastructure here in Idaho, Oregon, Washington, and British Columbia deliver. And we think it's an important part of our clean energy future, and it's technologies like this one that are going to make that happen. And so we appreciate your time today, Bob. And I thank everybody who's joined us for this webinar this month. And we look forward to seeing you in July.